All right, so let's look at some problems where we will attempt to calculate the free energy for a reaction, and then we can use that value to identify whether the reaction would be spontaneous or not under those conditions. So we want to calculate the standard free energy change for the formation of methane. And let me just point out, there's a typo there. I see now it's RXN is usually the way you would abbreviate reaction, and I've got the N and the X mixed up. So delta G, the naught symbol here is for standard state conditions, which is 25 degrees Celsius atmospheric pressure. Deviation from standard conditions is something we won't really go into, but this should be RXN. So we want to calculate the delta change for the reaction, delta G for the reaction, for the formation of methane from carbon and hydrogen at 298 Kelvin, and then determine from that value if the reaction is spontaneous under standard conditions. So we've got our reaction here, graphite, which would be as a solid, reacting with hydrogen to make methane. Now what I've put in here are some of the data from the textbook that correspond to the enthalpies of formation for the components and the standard entropies for the components. So we can use these to calculate the enthalpy change for the reaction and the entropy change for the reaction. And then once we have that, we can plug those in to calculate the free energy, delta G, for the reaction. So let's start with enthalpy. So the enthalpy change for this reaction, right? This will be the sum, oops, that was a bad sum sign, of the enthalpies of formation of the products minus the sum of the enthalpies of formation of the reactants. Right? So same as the formula we've been looking at so far. This works for enthalpy, works for entropy. We'll see. We can do this for free energy as well. There's also a free energy of formation that would apply to each molecule or atom in a reaction. Now, if we plug these in, start with the products. So the product here, methane, is minus 74.9 kilojoules per mole, and then subtract the sum of the reactants. Now, since both of the reactants are the elemental states of those compounds and the most stable allotrope of carbon in this case as well, those are all zero. So the sum of the reactants here is 0, and that's a pretty simple calculation. The enthalpy change for this reaction is minus 74.9 kilojoules per mole. And important to point out, the per mole is often left off of enthalpies, free energies, and it's just reported as kilojoules. So at a certain point, the per mole is kind of understood that you're referring to the reaction that you're describing. Now we can do the same thing for entropy here. The change in entropy for the reaction, again, is going to be sum of the products minus sum of the reactants. So there's a little more going on here. I'm not going to write out the equation again, but keep that in mind. But I'll use square brackets here again to separate the terms. So the product is methane. So the product, there's just 1 mole of methane. So that's 186.3. And again, this is entropy units, joules per k-mole, but I'm going to leave it off in the mathematical calculation. We'll make sure we add it in at the end. We're going to subtract the sum of the reactants. So 2 different reactants here. Carbon in the graphite form is 5.6. And we're going to add that to hydrogen. Gas phase hydrogen is 130.7. 2 moles of hydrogen in the reaction. So we've got to multiply that quantity by 2 because, again, that is on a per mole basis. So simplifying the terms here, this would be 186.3 minus 267 when we add all those together. And that gives us a entropy change for this reaction of minus 80.7 joules per k-mole. Right? Now, if we think about free energy, delta G is equal to delta H times T delta S, we're going to have to subtract that entropy term from that equation from the enthalpy term in that equation. So since the units are not the same, one's in kilojoules, one's in joules, it's always wise to change one of them And since free energy is in kilojoules, the best thing to do is take your entropy, change that to kilojoules before you plug in to solve for delta G. So if I divide by 1,000 here, that would move my decimal 3 places. This would be negative 0.0807 kilojoules per k mole. And then when I multiply that by the temperature, it'll be the same units, so I can add or subtract relative to the enthalpy to figure out the free energy. So once we have both of those values, delta G is equal to delta H minus T delta S. And so delta H here is minus 74.9 kilojoules per mole. And we're subtracting the term for entropy has temperature involved. So 298K times negative 0.0807 kilojoules per k mole. So if I multiply that out, so I kind of ran out of space here, but I think I can get it in the edge over here. This will be minus 74.9. This term multiplied out, it becomes 24. So minus negative 24 would be plus 24. 0.0 kilojoules per mole. So combined, we end up with a free energy for this reaction of minus 50.9 kilojoules per mole. And then the last part of the question, is this spontaneous under those conditions? And the answer is yes. Since that's a negative value for delta G, this would be a spontaneous reaction. Okay, now the second problem here, calculate the standard free energy change for the combustion of methane using values for standard free energies formation of reactants and products. Those, again, we can find in the back of the book. So combustion of methane would be methane gas plus oxygen gas. That would produce carbon dioxide and water. Right? And it's not balanced. There's 4 hydrogens here. We need a 2 here to balance the hydrogen, right? And then that would be 4 oxygen atoms on the product side. A 2 here would balance the equation. And for a problem like this, make sure you get a balanced equation before you go to do your calculation, because you'll need those coefficients. Now, just like with enthalpy and entropy, we can calculate the free energy change for a reaction from the sum of the free energies of formation of the products minus the sum of the free energies of formation of the reactants. Right? And if you get one thing out of this chapter, maybe it's being able to draw a sigma reasonably, although I've been doing this for quite a few years and I still struggle with the sigmas. Okay, again, we can find these in the back of the book, plug them all in, right? There's a lot of looking up numbers, plugging them in here, right? But it does give us useful information about our reaction. So the first product is CO2. So in the back of the book, that's minus 394.4 kilojoules per mole, just 1 mole in our equation. Combine that with water, so multiply by 2 here because 2 moles of water, and the standard free energy of formation is minus 228.6 kilojoules per mole for water. That's our products. Sum up the reactants, right, starting with CH4 or methane. Find that in the back of the textbook, that's minus 50.8. And then oxygen, standard free energy for elements in their most stable form is 0, similar to the way enthalpy is 0. So the oxygen contribution there is 0. So combine in the first set of brackets and we get minus 851.6 kilojoules per mole. And then we're going to subtract what we combine in the second, which is minus 50.8. Right, so 2 negatives there, we'll add 50.8 to minus 851.6, and that would give us delta G for this reaction is minus 800.8 kilojoules per mole, and that's negative, so that is spontaneous. Although it's worth pointing out again, right, if you just combine methane and oxygen, the reaction doesn't happen. You still have an activation energy that's required to get that reaction to start. But based on the energies of the reactants and the products, that is a very likely reaction. So it will happen under the appropriate conditions with the appropriate activation energy.